We talked about related rates. We talked about higher order derivatives. We talked about finding tangent lines and also velocity problems. Am I leaving anything out? Let me check. Oh, that's about it. Yeah. Okay. Any questions about that? You can use your notes on Friday. You can use your notes. You cannot use any kind of help from the internet or calculators or computers or whatever, except of course I've got to be able to see you, and you got to use your computer or iPhone or whatever to get in and take the test and to hand it in. But no help on the test with any kind of electronic device. Okay, well, let's continue talking about curve sketching. Oh, need to remember to record. Okay, now let's go to the shared screen. And let's finish that problem we started yesterday. Okay, so we were, somebody just came in, of course. We're working on this problem. We're finding the local maximum and minimum values of g of x equal to x plus 2 sine x on the closed interval from 0 to 2 pi. Okay, and we had gotten the critical numbers. So to do that, you take g prime, which is 1 plus 2 cosine x. So the critical numbers, well, this derivative is defined everywhere. So we don't get any critical numbers out of having the derivative not be defined. The ones we're going to get are, we get by setting g prime of x equal to 0. And we found that that meant that x was 2 pi over 3 or 4 pi over 3. We have our two critical numbers. And remember, this gives you all the places where the derivative can change sign. So I like to draw a number line, and this time we're only interested in the interval from 0 to 2 pi. So essentially, I'm ignoring anything outside that interval, okay, because of that condition in the problem. And then we got, let's see, 2 pi over 3 and 4 pi over 3. The two critical numbers. Okay, so we want to figure out what happens in between. Since we found all the places where the derivative is 0, that means that on each of these intervals, the derivative is either positive for all the numbers or it's negative for all the numbers. That's one reason you want to make sure you find all your critical numbers. If you don't, that's not always true. Okay, so since the derivative, we're looking at the interval from 0 to pi over 3. And since on that interval, the derivative is either positive or negative, all we have to do is check one point about pi over 4. How about this? which should be right about there. If I check it with pi over 4, well, 1 plus 2 cosine of pi over 4, the cosine of pi over 4 is 1 over the square root of 2. Well, I can't read. Okay, I can't read that. So try it. No, I don't want to. Okay. It'd be 1 plus 2 times 1 over the square root of 2. And actually, the only thing about that that's important is that it's a positive number. Okay. I get a positive number. So the derivative is positive on that interval. And that means the function is increasing. Between 2 pi over 3 and 4 pi over 3. Oh, pi over 2 is in there. So I could use that to check. Pi over 2. 1 plus 2 cosine of pi over 2. Cosine of pi over 2 is 0. So that gives me 1. So the function is, yeah, that's positive. The function's still increasing on that interval. Do I believe that? No. Okay, so what did I do wrong? Cosine of pi over 2 is 0, isn't it? Does anybody see what's wrong here? Well, look, let me look at this. Oh, wait a minute. Pi over 2's not in there. Okay. That's what's wrong. Pi over 2 is not in there. Pi over 2 is in this interval. Okay, so I must check pi is in there. Okay. Brain, please turn on. Let me erase that. All right. So pi is in there, and that makes a big difference. 1 plus 2 cosine of pi, well, that's equal to 1 minus 2 is minus 1. Okay, so that's negative. And that means the function is decreasing on that interval. All right, and then finally the last interval. Okay, what's the number between 4 pi over 3 and 2 pi? Can somebody give me one?
3 pi halves?
Yeah, I think that would work. 3 pi over 2. Okay, so let's see, I do my arithmetic down here. Well, at 3 pi over 2, the cosine is 0, so that's going to give you 1. Okay. That's going to give me a plus. And that means it's increasing on that interval. Okay, so I believe that looks better. All right, so what do we have then? Notice, just looking at the little sketch, at 2 pi over 3, it's going up and then it's coming down. At 4 pi over 3, it's going down, then it's coming up. So we've got a local maximum that happens at 2 pi over 3 and a local minimum that happens at 4 pi over 3. And I'm going to erase that. So G has a local maximum, G of 2 pi over 3, which would be equal, now this is back to the original function, 2 pi over 3 plus 2 times the sine of 2 pi over 3. And the sine of 2 pi over 3, okay, 2 pi over 3 is in the second quadrant. Sine is positive there, so it's going to be the same as the sine of pi over 3, which is the square root of 3 over 2. And that's equal to 2 pi over 3 plus the square root of 3. And that's a positive number, okay. Rough calculation, let's see. It's going to be a little bit bigger than 3 because 2 pi over 3 is bigger than 2, and the square root of 3 is bigger than 1, somewhere between 3 and 4. And well, sometimes you really need to pull out a calculator and get an approximation. But remember, I want you to leave your answers exact. And if you get an approximation, indicate that. And of course, on the test, you're not allowed to use calculators, so wouldn't be able to get one anyway. I designed the test not to need calculators. And then, yeah, so the local maximum is 2 pi over 3 plus the square root of 3. G of, okay, G has a local minimum G of 4 pi over 3, and that's equal to 4 pi over 3 plus 2 times the sine of 4 pi over 3. And sine of 4 pi over 3 is negative because it's in the third quadrant. So this is 4 pi over 3 plus minus 2 times the square root of 3 over 2, which is 4 pi over 3 minus the square root of 3. And let's see. That is 4 pi over 3 is bigger than 4 minus the square root of 3, about 1.7. So I think probably between 2 and 3, that number. Okay, but it's positive. Both of them are positive. And let's see, what else can we conclude? G is increasing. on the interval from 0 to 2 pi over 3 and the interval from 4 pi over 3 to 2 pi, and it's decreasing on the interval in the middle, which is 2 pi over 3 to 4 pi over 3. And let's get a rough sketch from just this information. This tells us a lot about what our function is going to look like. Let's see, I have G at the critical points evaluated. Okay, we get that number and that number. What is it at the endpoints? The endpoints are 0 and 2 pi. So G of 0, okay, it's x plus 2 sine x. So 0 plus 2 sine of 0 is 0. And G of 2 pi would be 2 pi plus 2 times the sine of 2 pi. Sine of 2 pi is 0, 2. Okay, so I've got the function evaluated at 4 points, the 2 endpoints, and and at the 2 critical numbers where we have a local max and a local min. Okay, so what does the graph look like? G of 0, 0. Let's see. I'll call that 2 pi. And so, and call that 2 pi. That point's on there. That's the 2 endpoints. G of pi, so call that 2 pi over 3. And I'll call that 4 pi over 3. At 2 pi over 3, we get a number that's larger than 3. And this one is actually less than 3. So, well, that makes sense. 3, okay, that's 2 pi is about 6.28. 3 should not be that high, call it. No. Okay. All right. About there. And then, except it's not 3. I shouldn't write that. It's G, that's G of 2 pi over 3. And then G of 4 pi over 3, put that below. So the function goes up, comes down, goes back up. And we squeeze then a fair amount of information out of what the graph looks like from what the first derivative does. Any questions about that problem?
No, Professor.
Okay. Okay, so we've done a couple of these finding local maxima minima and started looking at what that says about the graph. All this was from the first derivative. The second derivative also tells you about the graph, but it gives you different information. And well, we need to know what about something called concavity. Okay, so a definition. I'm going to talk about this. We're going to say that the graph of the function f is concave upward if no, okay, just f. F is concave upward if the graph of f lies above all its tangents on an interval I. Okay, that should go. It's concave upward on the interval I. Let me go back. Say this correctly. It kind of matters about the order in which you say things. Okay. It's concave upward on the interval I. If the graph of f lies above its tangents not legible. Okay. On I. Okay, so and concave down means it lies below. Got a picture. If f looks like this, okay, that's the graph of f. Notice that if I draw a tangent line at any place in that interval, so there, tangent line looks like that, tangent line looks like that. This function is concave up. Yeah, it's actually concave upward, but I usually just say concave up on I, and I guess I would be that interval. And I kind of think of it as it's like a smile. Okay. A smile. And concave down is a frown. Okay, so the function f is concave downward on the interval I. If the graph of f lies below its tangents on I. So okay. This one was concave up, concave down, like that. This is concave down. Because the tangent lines here oh, I said below. Oh, no, that's right. That's right. The graph is below. Yes. Okay. The tangents are above. Okay. So, yeah. Okay. So, this is going to tell us, well, how the graph is curving. And how do we figure out that? Well, that's what the second derivative tells us about. Concavity test. And I'm not going to prove this one for you. If the second derivative of x is greater than 0 for all x and I, then f is concave upward on I. If the second derivative is less than 0, for all x and I, oops, why did I write x? Then f is concave downward on I. Okay, so it's the second derivative this time. When the second derivative is positive, f is concave up. When the second derivative is negative, f is concave down. And that means that just like for the first derivative, we wanted to find the critical points. We're going to want to find, well, the critical points of the first derivative, actually. So set the second derivative equal to 0 or figure out where it does not exist and look at those numbers and then go from there and check intervals. But I'm getting a little bit ahead of myself. There's another definition I need to give you. Inflection point. A point P on a curve y equal to f of x is called an inflection point if the concavity changes at that point. That is, and P would be a critical point for the second derivative, okay? But so if it's an inflection point, if on the left-hand side of P, it's concave up, and then on the right-hand side, it's concave down, or vice versa, it's concave down on the left and then concave down up on the right. So if the concavity changes when the graph goes through that point P, you have what's called an inflection point. Okay. Let's take a function. Well, we pretty much have to go through the first derivative before we can get to the second derivative. But now we're going to do more than we were doing before. This is just a polynomial. So we're going to consider, I'm going to call it f of x equal to x to the fourth minus 4x cubed. Hardly legible. And let's find local minima and maxima. Intervals where f is decreasing and increasing. That's first derivative stuff. And then let's go further to find the intervals where f is concave up and concave down, upward, for short, concave up and concave down. Okay, and points of inflection. These problems get long. We can use calculus to get a good idea of what the current function is doing without plotting a whole lot of points. We find the high points, the low points, that's a local minima and maxima. We can find where it's going up, where it's going down. That's where the first derivative is positive or negative. So the first two things, this and this, from the first derivative. And the second two things, intervals where it's concave up and the points of inflection, that's from the second derivative. And after we've done that, let's sketch the graph. Okay, so that's a lot of stuff. Well, we don't have much of a choice but to go do the first derivative first. So first derivative information. And what is the first derivative? F prime is 4x cubed minus 12x squared. Right, okay, so, well, f was a polynomial, so f prime and f double prime will also be polynomials. And that means f prime always exists. So no critical points from f prime not existing. F prime of x equal to 0 would mean that 4x cubed minus 12x squared is equal to 0. And let's see, I can pull out an x squared factor because I want to figure out you want to get all the critical points. If you miss one, it's going to mess everything up, okay? Because you're not going to know where those changes occurred. So it's really important that you get all of them. I can factor out an x squared. I can also factor out a 4. Okay. And, oh, stop that. That's going to give me x minus 3. So 4x cubed minus 12x squared is 4x squared times x minus 3. If you see me make an error, please say something. It helps to find my errors early on and get them corrected rather than wait till the end of the problem when something doesn't make any sense. And you have to go back and find out where you went wrong. Okay. So, well, if 0 is equal to 4x squared times x minus 3, that says that either 4x squared is 0 or x minus 3 is 0. And both of those will give you that f prime is 0. The first one says x is 0 or x is 3. Okay, so we have two critical numbers. And they are 0 and 3. And this is for the first derivative. Okay. Here's my number line. And I'd like to remind myself what I'm doing. This is my number line for f prime, okay? I'll do another one for f double prime. My two critical numbers are 0 and 3. And the 0 and 3, that's the only places where f prime can go from positive to negative or vice versa. So that means that all I got to do is check a point in each interval. Okay, -1 is over there. And okay, I want to look at, let's see, remind myself what f prime is equal to. Okay, if I put -1 in to f prime, well, no matter what I put into that first factor, 4x squared, I get a positive number, okay? Get a positive number out of 4x squared. And -1, -3, that's the second factor. That's going to be -4. That's a negative number. So positive times negative is a negative. And that means that the function is decreasing on this interval. So do that in another color. Okay, so it's going. Okay, between 0 and 3, let's see. A number in there is 1. Check it there. If I put 1 in, I get, okay, 4, positive. 1 minus 3 is minus 2. That's negative. Okay, so the overall thing is negative. Now this can happen. Okay, you get a two decreasings in a row. Okay, so I'm still going down on that interval. And then something for the last interval. How about 4 is over there? Okay, if I put 4 in, well, 4 times 4 squared is positive. 4 minus 3 is positive. Now it's positive, so now the function is increasing. Okay, I'm going to go ahead and start a sketch, and I'm going to modify it after I get the second derivative information. Start my sketch. Okay. I guess I should figure out what's what first. Okay, so at 0. 0 is a critical number, but g of 0 is not a local maximum or minimum because the function decreases as it goes through 0. Okay, some critical numbers don't give you either a local maximum or a local minimum. But I do have a local minimum at 3. It's going down and then it comes back up. Okay, so g of 3, which is, what is that number? 4x cubed minus 12x squared. You want a point, or you want the highest point, so you put it back into the original function, okay? 4x cubed minus 12x squared. Let's go right down 4x cubed. And all of a sudden, I'm calling that G. We named it F. F of 0. F of 3. Okay. F of 3 would be 4 times 27 minus 12 times 9. Okay, I'm going to factor. I can pull a 4 out of both numbers. I can pull a 9 out of both numbers. And that leaves me with 3 minus 3. No. Oh, that can happen. Okay. 3 minus 3. 4, 3 cubed. Yeah, that's right. This is 0. Okay. So is that right?
I checked your multiplication, and that's right.
Okay.
Do we plug it into the F prime or to the F?
To the F. Okay. Yeah. You have to keep these things straight. I plugged it into F prime. Of course, it's 0. It's a critical number. I'm supposed to put it back in F, x to the 4th minus 4x cubed. Yeah, so this is an example of something you do not want to do. F is not this function. It was, yeah, you want to put it back in the F, not F prime. Sorry. If I look at the wrong line, don't check too carefully, do these kinds of things. Okay, yeah, there's the original function. And that makes a big difference. It can happen that your local minimum is at 0, of course, but it's not true here, I don't think. Okay, so that means 3 to the 4th minus 4 times 3 cubed. And it's easier to do the arithmetic if you factor. That's 3 minus 4. So that's minus 27. Okay. Okay, so nothing happens at 0, but I'm going to get, what is f of 0? F of 0 is 0, right? And there, the function's right there. F of 0 is 0. It's not a local max or min, but minus 27 is a local minimum. Okay. And that means that I also know that F decreases on minus infinity up to 3. Remember, it just kind of goes through that 0, 0 and keeps decreasing. There's supposed to be an infinity. And increases on 3 and up. Okay, so what do we know so far? F of 0 is 0. F of 3 is minus 27. I'll put it there. And F, okay, it's decreasing. And then it starts increasing. And it's a polynomial. So it's going to go up to infinity as x goes to minus infinity or x goes to plus infinity for this particular function. Okay, that's as much information as I can get out of the first derivative. Now, and I'm going to modify my graph after I get the second derivative. Okay, what the second derivative tells me about my function. Okay, now I do need f prime. F prime was 4x cubed minus 12x squared. Okay, f prime was, let's check it one last time. Make sure I got the right line. Yes, f prime is 4x cubed minus 12x squared, which means that f double prime is 12x squared minus 24x. And so I won't have to go flipping through again. Let's write down f. F is x to the 4th. Okay. Okay, so there's our second derivative. And I want to find the critical numbers for the second derivative. So set it equal to 0 or find where it doesn't exist. This is a polynomial. f double prime always exists. I guess I'm not going to have time today. We're going to see one where f double prime doesn't always exist, and neither does f prime. Okay, but that's later. This one exists for all x, and let's see. So that means the only critical numbers we'll get, but it's by setting f double prime equal to 0. And again, it really helps if you factor. And can factor out a 12x, okay, times x minus 2. Saying something's equal to 0 is easier if you factor it. If you're taking the derivative, it's easier if you don't factor it. So yeah, what the form you're going to want these functions in depends on what you need to do with it, whether you need to differentiate it or set it equal to 0. And there'll be lots of other things coming up that we're going to use this stuff for. But okay, so, but this happens at two numbers when x is 0 or x is 2. Okay, so I've got two critical numbers from my second derivative. Let's put that there so I remember what the number line means. 0 and 2. And since we found all the places where f double prime is 0, what happens in the between's got to be either all positive or all negative for the second derivative. Okay, so again, you just check one point in each interval. How about -1? If I put -1 into the second derivative, I get, well, 12 times -1 is -12. That's negative, and -1 minus 2 is negative. So that's positive, which means the graph is concave up. Okay. If I check the number between 0 and 2, so 1's in there. 12 times 1 is positive. 1 minus 2 is negative. That's going to be negative. So the graph is concave down on that interval. After 2, how about 3 over there? That's going to give me positive. So positive. So it's going back to being concave up. So what we've got, f is concave up on minus infinity to 0 and on 2 to infinity. And f is concave down on the interval in between. Okay, and that means we have, okay, the concavity changed from up to down, so here to here, it changed. That means 0 f of 0, which is equal to 0, 0, is a point of inflection. And so is 2f of 2. At 2, it went from down to being up, which is 2, and f of 2 would be 2 to the 4th minus, okay, 2 to the 4th minus 2 to the 5th, basically. Which is 16 minus 32, so 2 minus 16. Okay, so we have some more information, and how does this change our graph? Well, I'm going to put 2 on there, and okay, call this minus 16, and maybe I'll color this a little bit different color. How about a nice purple? Okay, oops, nope, not there. And I didn't want to erase. Okay, well, I erased it. Heck, why not? Maybe I'll just erase the whole thing. Okay. Oh, and I'm out of time. Okay. Well, maybe I'll just stop here. We will finish this problem. Well, we're going to review tomorrow. Test is Friday. No, your minds are on the test anyway. Should be. Okay. And we will finish this problem on Monday. But I'm definitely out of time, so you can go. Class is over. Hang around if you've got a question.
Bye.